In this video, I just want to model one of the Young's double slit experiment equations. We're doing the first one here. It's number 14. So a 600 nanometer laser beam. Okay, well, stop right there. What's that? This is all about identifying the right variables. That is the wavelength of the laser beam. So I'm just going to write that down right away. Oh, 600, not 400, excuse me. 600 nanometers. And the next thing I'm going to do, mentioned this before, is everything is going to have to be in the same units. So I'm going to want to convert that. So I'm just going to convert that right away to meters. I'm not going to put it in proper scientific notation. I'm just going to get rid of the nano, put in times 10 to the negative ninth, and call it a day. So next is incident on diffraction grating with an average slit spacing of 0.2 millimeters. That is D. 0.2 millimeters. So a diffraction grating. Remember, that's not a double slit, but it's thousands and thousands of slits. Oftentimes, though, that's not the way diffraction gratings are described. I hinted at this in the previous video, but often, like for example, the one that I had 7,000 lines per millimeter is the way that that one was phrased. So what would be the average slit spacing for that? Well, I would do 1/700th of a millimeter and throw that in my calculator. Okay, and I would get, that would be 1.43 times 10 to the negative 3 millimeters, and then I would need to get rid of the milli, so that'd be 1.43 times 10 to the negative 6th meters. Like insanely close together. So that's actually on the order of micrometers. Anyway, not true for this one. The resulting pattern is seen on the screen that is placed 2 meters from the slits. So that's the definition of L, the slit to screen spacing. So what is the spacing between the central maximum and the first order maximum? All right, well, it's the first problem, so it's kind of trying to get that for us in a nice simple way. What that's asking for is, what is X? And so we know that X is equal to lambda L over D. So I can put that into my calculator here. All right, let me plug in. 600 times 10 to the negative 9th meters. L is 2.0 meters, all over D, which is, oh, I didn't convert this, 0.2 times 10 to the negative 3rd meters. I'm not even going to bother putting anything into proper scientific notation until the final answer. Because the less work you do on that, the more work you do on that, the more likely it is you're going to make an error, especially when there's no need to do any more work than what I've just done. Okay. So I throw that into my calculator, and I get the answer is 6.0 times 10 to the negative 3rd meters, or if I wanted to just convert that, 6 millimeters. Now I'll tell you, just for developing intuitions, lambdas are going to be on the orders of hundreds of nanometers if it's visible light. D tends to be millimeters or less than millimeters. Length of slits to screen, that tends to be in the order of like half a meter to a couple of meters. And how far apart are our maxima? You know, millimeters to centimeters is about normal for that, just so that when you get an answer, you can go, oh, okay, that feels right or that doesn't feel right. So next, B. What is the space between the central maximum and the first order minimum? Oh, okay. Well, this is about knowledge of the pattern. So if this is my central max, here's my first order max, second order max, third order max, and then on the other side as well. And it's asking about the first order min. In the other video, we said that the minima, the exact point of the minima is going to be equidistant between the exact points of the maxima. So this is just half X. So I don't really have to do any work except for this part of the problem. Realize that B is looking for half X. So if I find half X, that's just going to be 3 times 10 to the negative 3rd meters. Right? So this question is more about knowledge of the pattern. C. What's the spacing between the central max and the second order minimum? All right, so that would be here. So if I just count it out, that's X and then another half X. So that's just 3 halves X, or 9 times 10 to the negative 3rd meters. So a knowledge of the pattern oftentimes is important. Sometimes in the given information, they tell you something like the distance between the fourth order maximum and the second order minimum is this. and you have to realize, oh, okay, well, that's some multiple of x. I need to look at the pattern and figure out what multiple of x is, because that's a roundabout way of telling you what x is for that problem. The last thing, compared to the intensity of the first order maximum, what would be true about the intensity of the second order maximum? Well, we saw that in the video, it is less, but I did want to talk a little bit more about that. And that's kind of really one of the main points why I wanted to do this video. So if I call this, if this is along the screen, and I have an axis here, and I call this axis an intensity axis, we know that the first order maximum, or excuse me, the central maximum is going to be here. The first order maximum is going to be x away, and x away on this side. The second order maximum is going to be, once again, x away and x away, right? Third order maximum, x away. That all of these things are equally spaced, x, 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 right? As long as the spreading is not that far, that we're reasonably close to the central maximum. Okay, but let's just assume we are reasonably close to the central maximum. Here we go. And that means the minima are going to be equidistant between those. Okay. Actually, let me just use my red pen here. Okay. So minima, minima, minima. If I wanted to plot the intensity as a function of position here, this is what this would look like. At the central maxima, I have the highest intensity, then nothing here at the minimum. And it kind of fades from here to here. Then at the first order maximum, it's going to be less than at the central maximum. So first order maximum is going to be less than 0. And the second order maximum, even less. But I'll tell you, the even less bit, it is not a linear decrease, right? In fact, the pattern for the intensity as a function of position looks like this. And then it's symmetrical about the central maximum, right? Whereas if we were to look at what this function is that connects the top of the points, it's actually an e to the negative x, right? It is a weird sort of exponential decay. It's not a linear decay. And in fact, this shape here, you can imagine, is a bell curve. And so these things are just sort of nested inside the bell curve. And the math of proving that is really ornery and really nasty, but it is interesting, and I wanted to just show you what that looked like. So by varying the parameters in the problem, I can space out where these maximas are. You can see also when I did the experiment, you notice I got really defined points, and then there was lots of dark, and then another defined point. But when he did it, it was more like a blur of light. And that's actually the difference between doing a double slit. This might be the graph for a double slit. With a diffraction grating, when you have more slits, right, it doesn't, as long as the average slit spacing is the same, it doesn't change the pattern. What it changes is how clearly defined the pattern is. Let me just translate my axes markings down here. Okay. In other words, the maxima will be, assuming that d is equal in both, L is equal in both, and lambda is equal in both, therefore x has to be equal in both. But what's different is how sharp these peaks are, right? So instead of the pattern gradually going from the max to the min, what ends up happening is something like this, is that you have these like little spikes. So that's what the pattern looks like, that it looks pretty much dark in between. It is a decay, but it's a very sharp decay down to a quick 0. It remains at 0 for a long time and then quickly spikes back up. And that's why with the diffraction grating with many slits, I would see just dots, right? So this is many slits, and this is 2 slits. In fact, in class, I would have been able to show you what the pattern looks like with 2 slits, and then 3, then with 4, then with many, and we could see those maxima getting ever more defined and defined and defined. Rather than being a blur of light, it becomes and converges on a dot of light. So that's a modeling of problem 14. Remember, just going back to the basics, it's about identifying what you have, it's about doing unit conversions, and it's about a knowledge of the pattern. In other words, another thing about the knowledge of the pattern is remember how far out it is from the central max also lets you know something about the path difference in terms of multiples of lambda to that point.